Hey there, welcome back. We're going to be actually continuing Unit 3, but now we're going to start looking at solutions. So today's all about just some general information about solutions, things you ought to already be familiar with. Here we go. So solutions are homogeneous mixtures. The prefix homo there means same, geneus means made up of, so kind of self-explanatory there. Get this, a solution is so well made, it's the same from top to bottom, left to right, front to back. There's no like chunks floating at the bottom or swirling around inside or anything like that. Solutions can be solids, liquids, or gases. All three of those are possibilities. Bronze is a good example of a solid solution, and the air you're breathing right now is a good example of a gaseous solution. Now, all solutions have at least two parts. There's the solvent, and then everything else is the solutes, the things being dissolved. Solvent being the thing that does the dissolving. Now, what if you don't know which is which? Well, we actually have a rule for that. We say the thing you have the most of is the solvent. So I have an ingredient label from one of my favorite sodas, Cherry Coke Zero, and you can see all the ingredients in there. And here in the United States, the ingredient labels are designed to start with the thing you have the most of. So in the terms of a soda, where it is definitely a liquid solution, it's really easy to tell what I have the most of. I have the most of the thing in the beginning here, carbonated water. And in fact, actually, the carbonated water itself is a solution. That's carbon dioxide dissolved in water. I have certainly more water in the soda than I have carbon dioxide. So truly, it's the water that is the solvent, and all of these other ingredients are then solutes. It's the way we define these things. Now, things you need to know about solutions, and I hope this is kind of a duh moment. You probably already realize these things, but let's make sure. Solutions can't be filtered. Okay, now imagine if I had an enlargement of a piece of filter paper. Okay, what I'm seeing the filter paper is there's holes in the filter paper. Now those holes are really tiny, and so it lets things that are really small through and things that aren't small get caught. But that's what a filter is. Now a solution, remember I said it's so mixed up, like there's no parts to it that you can see. Everything, even the solutes, are so small it would go right through those holes, all of it. You would get nothing caught in your filter paper. So we can't filter it. It's not going to scatter light. Now colloids do that, and that is one of our tests for colloid is if it scatters light. Don't know if you've ever noticed how when you're driving to work or school or anywhere and it's a foggy morning and you've got your headlights going, you actually get to see the beams coming out from the headlights before they hit the road. That's the Tyndall effect, getting to see the beam of light. If it was a solution, if you were driving through a solution, I hope not, because cars aren't meant to drive through solutions, but if you were driving through a solution, you know, like a big giant vat of Cherry Coke Zero, you would not be seeing any headlight beams. It would just be a circle where the headlights are hitting. Okay, and then also solutions will never settle, never settle. So if it eventually settles, it's not really a solution, it's a suspension. So be aware of what they are by also being aware of what they're not. They're not suspensions and they're not colloids. All right, let's clear away that and talk about big deal with solutions. How do I know if I'm going to get a solution? How do I know if this is going to dissolve in this? We have a rule like dissolves like. Now you can never, ever, ever say that on the test and get points. That's not a reason to say, you know, are these two going to make a solution? Explain your reasoning, and you're like, yes, they will, because like dissolves like. Sorry, you lost your points. It's not going to happen. What you need to understand is that's just a little shortcut way of saying the more alike the solute and solvent are in terms of their intermolecular forces, then the more likely the solute will dissolve in that solvent. Okay, so reminder of the intermolecular forces: hydrogen bonding, dipole, dipole, London. Okay, so we're looking for things that can do hydrogen bonding or polar molecules or nonpolar molecules. So why do oil and water not mix? Well, water can do all three, but the strongest of that for water is hydrogen bonding. Oil can't do hydrogen bonding, and oil's not even polar usually. Oils are usually considered nonpolar, and so they can only do London dispersion forces. Well, they're very different in their IMFs. Yes, water can do a little bit of IMF, of London dispersion forces, but it really is set up for hydrogen bonding. So oil and water do not mix well at all for that reason. Now, if I throw some dish soap into it and stir it up, I'm going to see them mixing a lot better. So what must be true about that soap? That it can mix with both the oil and the water. Yeah, you guessed it. Soap has two parts to it, two sides. One part is nonpolar, one part is polar. So the nonpolar part will dissolve in the oil, and the polar part will dissolve in the water, and it can literally connect the two. And then we will see we don't get that separation of the oil and water like we used to. Other things that do that are often called emulsifiers. And soybean oil, there's something to soy lecithin. That's the part I'm trying to think of. Soy lecithin is a great agent for doing that. So if you read in an ingredient list anything about soy lecithin, they're using that as an emulsifier, something that will keep the oils and the waters together and not let them separate, because sometimes, you know, separated oils and waters taste disgusting. I mean, I like mayonnaise on a sandwich, but if you just handed me a jar of oil and water, which is the major ingredients of mayonnaise, it's not going to be tasty. Okay, using the egg yolk, which have the emulsifiers and then the other seasonings they throw in, and blending it all up, that's what makes it tastier, and that's why I want it on a sandwich. Okay, so we know why some things will dissolve in other things. Let's talk about how well they will dissolve in things, okay? To show this, we usually show, just in general, we can say it's saturated, unsaturated, or supersaturated. And you can see the definitions there. Saturated is dissolved as much as it can. That's it. It's done dissolving. If you add any more, it's going to sit at the bottom. So it's actually no longer a solution. Suspension if it's sitting at the bottom, just saying. Okay, unsaturated means you can dissolve more. How much more can you dissolve? Yeah, no one knows. It's just, it can dissolve more. That's all we know. And then supersaturated is one that has almost been tricked into dissolving more than it should at that temperature. Now, this is all temperature based. So to show how this all works out, we often show this, a solubility curve. Okay, so for the solubility curve, what we see going on here is we see temperature is seen as a factor, and then how much will dissolve is the other factor. And so you can see most lines go up as temperature goes up. And we know this from experience. If I want to dissolve, especially solids and liquids better, if I warm up the liquid, it's going to dissolve better. And if I make hot cocoa, and of course I want it hot, so I use hot water and I stir it up, it seems dissolved. Well, I take, drink like half of it, and then when my kids comes and needs my help with something, so I set it down, I go off, 20 minutes later I come back, my hot cocoa is no longer hot, but it's still tasty, so I drink it. Well, what do I notice at the bottom? I notice now I have a lot of undissolved stuff at the bottom, because in the decreasing temperature, the solubility has decreased. So typically, especially for most solids and liquids, the amount that can dissolve will increase. The solubility will increase with increasing temperature. Now, there's a few lines on here where that's not the case. And I want to point this one out specifically. This is NH3, this is ammonia, and this is a gas. And this is very characteristics of gases. They do not dissolve well in liquids, and they do not dissolve well the hotter you get the liquid. You would actually cool down the liquid to get it to dissolve better. Gases really do not dissolve well at all. We're going to come back to that in a moment. But that's a solubility curve, easy points. Like if I'm like, what's the solubility of sodium nitrate at 10 degrees Celsius? So I go to 10 degrees Celsius, I go up to where, oh, right there. The max of sodium nitrate that I can dissolve in 100 grams of water is 80 grams of sodium nitrate. Now that's a lot. That's really soluble. Okay, in comparison, something like, I don't know, sodium chloride, you know, salt, which is still pretty good, that's only 37 grams. So on the line tells you the limit of solubility, that's saturated. If I was below the line, say sodium nitrate could dissolve 80, but I only put in 60. So I'm below the line here, unsaturated. I can dissolve more. Say somehow I messed with it, I was very mean to the solution and I got to dissolve 100 grams, but it really should only hold 80. Then it's supersaturated. Now, supersaturated is not natural at all, but we can often kind of manipulate things to get it to do that. Normally, it involves warming it up, dissolving extra. I could warm it up here to 35 degrees Celsius and get 100 grams to dissolve. And then if I very carefully cool it back down to 10 degrees, I might be able to get that extra to stay dissolved. On the other hand, I might, like my hot cocoa, see the extra start sinking to the bottom. It's either way there. Okay, so that's the general terms: saturated, unsaturated, supersaturated, and the solubility curve. I've never seen a solubility curve on the test. That doesn't mean there couldn't be one. It would be easy points if it was. You just, you know, read stuff right off the graph there. So total possibility, but not usually the direction that AP chemistry ends up going. But wanted you to see that just in case you've never seen one. Okay, let's move on to other factors we're going to discuss that affect how well or fast. I'm mostly now going to be talking about how quickly you can make that solution: particle size, pressure, and agitation. Okay, so particle size is a big deal. It makes sense if you think that I put a big solid chunk of something in, say, water. Well, the water can only attack the outside of that solid chunk because that's the only part the water can touch. So it takes time to pull away the outside layer and expose an inside layer, to pull away that inside layer to expose the next inside layer. And that's why it takes a while to dissolve things, okay? So they do often ask this on the AP exam, so I wanted to be sure that we go over an example of this. Now I have an official drawing here, okay? But that's not usually what they ask for. So I'm going to do it here. So water I'm going to represent as a molecule that looks like this. And oxygen is always the negative end because it's very electronegative. And that leaves hydrogens to be positive. They're electropositive. Okay. Sodium chloride, I have a little tiny sodium I'm going to put a plus sign with, and a big chlorine I'm going to put a minus with. Now, usually they'll say, show something like, I don't know, they might say 12. Wow, I'm going to match this up incorrectly. There we go. 12 sodium chlorides. Okay, I'm going to go with 9. They'll usually tell you a number. If they don't tell you an exact number, then we take a wide range of it. Okay, so all these little ones are positive. All the big ones are negative. I'm not going to fill them all in, but that's exactly what's going on. Big ones are negative. Little ones are positive. Sodium is positive, surrounded by negative chlorines. Chlorine's negative, surrounded by positive sodiums. But what happens as it dissolves? Well, first off, water comes around it. Around this sodium here in this corner, what would be attracted to a positive? The negative side of water, and I draw a little line like that. Usually they want a dashed line, but sometimes they just want a solid line. Something like that. What would be attracted around this negative? Something positive. So I would draw one, or we usually do take both hydrogens being attracted there. Okay, so that's a possibility. What if the chlorine's already been broken off? What should be around the chlorine? Around the chlorine should be a whole bunch of waters, but those waters should be where the hydrogens, the positive part of water, are always very close. That's supposed to be touching, sorry. Very close, draw little lines, very close bonding, polar kind of bonding. That's a negative ion, and water's a polar molecule, and the positive part of water will be attracted to the negative ion. That should make total sense, but it is Coulomb's law as well. And then maybe here's a broken off sodium, tiny little positive ion. What's going to be attracted to it? Whole bunch of negative oxygens. And so I'm going to, and then quickly draw on my little Mickey Mouse ears to finish them off. If you've never seen water as a Mickey Mouse head, then good for you, I guess. Okay, so there we go. That is often the way they want. Like they have asked that a lot on the test. This may not be sodium chloride, but it's a very similar situation. You have an ion that has positive and negative parts, and they want you to arrange the water correctly around it. Now, the one I graded a couple years ago, they even gave you the picture of it all done. They just said to draw the connections. We took so many weird random lines all over. As long as you pretty much put a positive with the negative, we took it. So this is often how exactly it'll look. I can't say, but I would be surprised if something like this or similar to this was not on the free response. It'd be a little surprising. They tend to like this kind of question a lot. So there you go, some easy points for you to get just by doing some little drawings. As long as you can remember positives to negative, negatives to positive, you're good to go. Okay, so by the way, if I crush up a big chunk, break it apart in little pieces, you know, hit it with a hammer before I put it in or something like that, use powdered sugar and not regular sugar, then it will dissolve faster because I have more surface area. Lots of small pieces have more surface area than one big piece. They'll all have the same volume. I'm not changing the volume total of everything. I am changing the total surface area. Okay. Another thing that affects gases only, though, is the pressure. The pressure above a liquid would influence how well the gas dissolves in the liquid. Lots of pressure, lots of dissolving. A little bit of pressure, a little bit of dissolving. You don't need to know Henry's law. Okay, but that's what it says. You do need to know lots of pressure above would mean lots or usually more able to dissolve it below. Now we have one, because gases don't like usually being dissolved. Now there's one gas that doesn't mind quite so much being dissolved. Do you see how I'm trying to qualify that? It still does not dissolve great, but it doesn't mind it quite so much, and that's ammonia. Why would ammonia be okay dissolving in water? Now, notice what I'm saying. I'm saying NH3 is okay being in H2O. Do you see why? Do you see why? You should be able to answer this already. Water does hydrogen bonding and ammonia does hydrogen bonding because it has that lone pair on the end, and we know water has 2 lone pairs on the oxygen, okay? Very, very, very similar intermolecular forces of hydrogen bonding. So ammonia is one of the better gases to try to dissolve. Still doesn't dissolve super great, but like where the rest of the gases really are awful at dissolving, ammonia is okay. All right, and note, I just applied what you already knew about intermolecular forces to explain why it's better than other things. That's typical of a question they could ask on the free response portion. They'll tell you this one is better to dissolve in water than this one, explain why. There you go. Okay. And I do want to point this out because we've already discussed gases and partial pressures. By the way, the greater the pressure of that gas above the liquid, the more likely that gas will be in. Okay, if all of these dots are nitrogen, then yes, nitrogen will dissolve. If only this dot and this dot is nitrogen, I'm not going to get a lot of nitrogen dissolving. Okay, just because I fill it full of argon does not mean I'm going to increase the rate of the nitrogen dissolving. All right, so mathematically, you don't need to know Henry's law, but it should make sense. The more molecules there are above, the more pressure there is above, more likely they're going to move down into and dissolve into the liquid. Okay. Next up, let's talk about agitation, stirring. Stirring helps solids dissolve in liquids for this reason. You see how this is the small one. So sodium is hydrated, okay, or solvated, okay, it's surrounded by water. If I stir, it pushes this whole chunk of stuff away. And that makes room for water that hasn't dissolved anything to come in and start attacking the sodium chloride. Same thing going on here. So all these other empty water molecules, if I stir, moves the full water molecules away, the ones that have already solvated some sodium chloride get moved away, and the fresh solvent comes in. Now, do not agitate gases in water. Again, they really don't dissolve well, and if you stir them up, it makes them undissolve, not dissolve. So don't touch it. Don't shake. Well, you know not to shake a can of soda and then open it right away, right? Why is that? Because all that gas will suddenly undissolve and it'll push soda out with it. Not a good thing. It is fun if you're doing, you know, Mentos and Diet Coke, but beyond that, you don't want to. Okay. There are ways to separate the parts of a solution. Now let's talk about, first off, we said this, but let's circle back. Filtration is not a way to separate the parts of a solution. That's not going to work. You cannot use filtration. Again, you should know why. The parts of a solution are so tiny and so well mixed up, everything would go through the holes that are the filter. But one way that will work is paper chromatography, also known as thin layer chromatography, because the paper is a thin layer. But it could be done with a layer that's not paper. That is a possibility. I do remember in my just my bachelor's work in chemistry, we had, oh, I want a different color. I'm going to file it this time. We had plastic films, plastic sheets, and they were coated with this white coating. And if I like rubbed too hard, I would rub off the coating. So we handled them gently, but we did the same thing with paper chromatography. It just, we could choose what to coat the plastic with and then pick how well. If you chose well, you'd get them to separate well. And if you didn't choose well, then they didn't separate well. So we've already discussed how paper chromatography works. That was back in our bonding review in an earlier unit. Thin layer works exactly the same way. Paper chromatography is a type of thin layer chromatography. They really are very, very much the same thing, okay? Thin layer is just a general category. So don't freak out if you hear thin layer like, oh, we don't know about thin layer. Yeah, you do know about thin layer. You know about paper chromatography, and the exact same thing works with thin layer. Thank you. Okay. Clearing that away. Another way to separate is column chromatography, very similar, but now, and I did this a lot in college. It almost seemed like this was the only way in one of my classes that they wanted to do separations. You put a mixture in the top and you have some special packing, I think we just normally call it column packing, some special ingredient that some of the molecules stick to well, but the others don't. And then as they literally slowly by gravity pull through and drip out this other side, you can see they're starting to separate. So eventually the yellow here is gonna like win, it's gonna go through first, and I would have yellow in the beaker. And then as soon as I see all the yellows caught, I move out that beaker and put in a new one. And then the next layer comes flowing through because of gravity, and I can catch that in that second beaker. And then I can move that out of the way and put in my third beaker. And the next layer eventually with gravity comes through. And so that's column chromatography. Again, it separates things based on how well they form those intermolecular forces with what's in the column. If they do it well, they're going to be in that column a long time. They'll be like in the last beaker you catch. If they don't make good bonds with what's in that column packing, then it's going to come out one of the first sets. So that's column chromatography, just another form of separating based on intermolecular forces. So thin layers, intermolecular forces, column chromatography, intermolecular forces. A way to separate when we have a solid that's been dissolved in a liquid is to evaporate the liquid. So here is just a picture. I mean, this is the way we get sea salt. If your salt container says sea salt, literally someone is dumping buckets of ocean water onto a big flat area where the sun dries it out, and then they scrape the salt up. They've evaporated the solvent and it's left the solutes. I mean, this would work if I leave out a cup of Kool-Aid. Just let it evaporate in my kitchen. After a while, I'm only going to have the sugar and the Kool-Aid powder left in the cup. As long as it hasn't like gone moldy, I could actually add water and get back the Kool-Aid because all I've done is removed by evaporation the solvent of water. Now, if I want to do it faster, I heat it up. So I put it in a warm pot, and eventually all the water evaporates and I have nothing but the solid left. And then I turn off the heat real fast, or that starts burning. That is kind of a danger if you do it that way. So you got to be careful if you're not just letting it evaporate. Freeze drying is doing the same thing. It is getting the water or the solvent to evaporate, but not increasing the temperature, and that way what you're left over with is not going to burn, like making powdered milk. That's exactly how they make powdered milk. Okay, and then the last one I want to discuss is distillation. Okay, so distillation also works on intermolecular forces, but it works on intermolecular forces between liquids. Distillation is very useful for a mixture of a liquid. So you have this liquid and this liquid and this liquid, and they're all mixed up, like in crude oil, which we get out of the ground. Okay, you put your mixture, whatever that mixture is. I'm going to get a fun color here. Let's go dark blue. You put your mixture in the flask, the distillation flask there, and you start heating it up. Now, here's the thing. This works if the liquids that are mixed have different boiling points. Why would they have different boiling points? You already know this, because of different strengths of intermolecular forces. The ones held together really strong are going to need a high amount of heat, have a high boiling point. And the ones held weakly, maybe only London dispersion forces, are going to boil pretty quickly, have a low boiling point. So you put your mixture with different IMFs to make different boiling points in there, and you just start heating it up. And you heat it up, and eventually you'll see some boiling happen. That's that lowest one, the one with the weakest IMFs boiling off. Now it turns to a gas, because that's what boiling does, turns the liquid to a gas, and it then goes through this condenser, which is jacketed, like the whole thing, 360, this is a cutaway view, is coated with cool water. So it takes the gas and it cools it down to where it drips out as a liquid again, and you just catch it in that flask. And then eventually the boiling is going to stop, because all of that compound has boiled away and been condensed, and you could take that flask of pure liquid with the lowest boiling point and do something with it. Then you put in a new flask to collect with, and you make it hotter over here. You turn the burner up higher, and you get it hotter, 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 and now it's going to boil again. And now the second weakest, strongest, or the one that's slightly stronger bonded with intermolecular forces, that's really what I'm trying to say there, is going to start boiling. And again, you cool it down and you can collect it, and then eventually it stops boiling because you've collected it all, and you can move that off to the side. And then you heat it up hotter, and now you get the next one, the one with the next strongest intermolecular forces. And then after that one's gone, you heat it up stronger and you get the next one, and so on and so on and so forth. So if I were to do this like in my garage, maybe I buy a barrel of crude oil and I'm going to make my own gasoline. Well, crude oil has a lot more than just gasoline in it. So I put in a huge distillation apparatus and I start heating it up. First thing I'm going to drive off is things like natural gas and maybe propane, things like that, okay? Then eventually, because those have weak intermolecular forces, they're all nonpolar, and they have small molecules, so small amount of electrons, not many London dispersion forces. Gasoline has low to medium amount of intermolecular forces. So I'm going to have to go through lots of boilings before I can finally get to like octane, which would be considered gasoline. But then truly I could get 100% pure octane in this flask here and drop it straight into my gas tank. Now my car is not necessarily meant to have 100% octane rating. It's not going to do a huge amount of damage to my car engine, but it's not something I want to be running off of all the time. Okay, but I could catch all the parts that is in gasoline, which is usually a whole lot of parts, and I could just pour it straight into my gas tank. But I still have other things in there even after the gasoline. There's the jet fuel part in there. There's naphtha stuff in there. There's all sorts of really long hydrocarbons that have lots of electrons and have very strong amount of London dispersion forces and are going to take a lot of heat before they even boil away. But it's absolutely totally the way. Like if you go to an oil refinery, this is what they are doing to that oil. They are heating it up and they are getting the layers to separate based on their strength of intermolecular forces. The weaker the amount of forces, in this case, the total amount of London dispersion forces, the quicker it will boil away. And then they just make sure to catch it. And then the next one, and they make sure to catch that. And then eventually they're left with nothing but the strongest intermolecular force held together ones, and it'd be pure in that distillation flask by the time I boil away all the others. So a great way to separate liquids as long as they have very different intermolecular forces. If I have one that has very similar amount of London dispersion forces, not going to work well at all. If the boiling temperatures are like 74.1 and 74.2 degrees Celsius, I'm not going to be very successful separating that. But I have something like water, which can do hydrogen bonding, and then oil, which can't do anything but London dispersion forces, I'm probably going to be very successful separating that with distillation. The greater the difference in intermolecular forces, the greater the difference in their boiling temperatures, the easier it will be for distillation to separate. Okay, that is really it for just our crash course review. This should honestly all be a review. It wouldn't surprise me if it's not, that's okay. But this is just an introduction to solutions I wanted you to have. We've got some practice to do in Canvas, so get into Canvas, work on your practice quiz. Good luck, and I'll see you next time.